Okay, is my screen is visible?
Yes, sir.
Yes, sir.
So we have seen some standard functions like we have seen unit step. We have also seen ramp function, and we have also seen parabola, a parabolic function. What is the unit step function?
सर आवाज नहीं आ रहा है.
But right now I'm in university. I'm using the Wi-Fi of university campus. So
सर आई थिंक आपकी ये माइक्रोफोन में कुछ प्रॉब्लम है.
नहीं माइक्रोफोन में प्रॉब्लम नहीं है.
हेलो.
Anyone else is having the same problem?
Yes, sir.
Yes, sir.
यस सर अभी ठीक
Yes,
है.
sir.
Sir, now it is
Me too,
clear.
yes.
When you are
Now it is clear.
speaking
When you
and
are
teaching,
teaching,
then it is
teaching,
problem.
then it is not clear, sir.
Okay. Let's give it another try. So we have seen a few of the functions, that is standard functions. First one is unit step function. It is denoted by u of t, and we have seen that Laplace transform of u of t is how much? 1 upon s. And how
Yes,
does
sir.
that function look like? It is look like this, right? And ramp function is denoted by small of rt. And what is the Laplace transform of rt? What is the Laplace transform of r of t? That is ramp function 1 upon
1
s.
upon x square.
How does ramp function look like? It looks like this, right? Next function is parabolic. You can write it as pt. And we have also seen what is parabolic. That is Laplace transform of parabolic function is given by 1 upon s cube. And how does parabolic function look like? So it looks like this, right? It increases non-linearly, right? All these are time domain or time axis. We will see one another signal which is very important as far as this control system course is concerned. So that function is called as impulse function or impulse signal or function, and it is denoted by del t. Am I audible clearly now?
Yes, sir. Now it is clear.
Yes, sir.
Yes, sir.
Okay. So it is represented by del t. And what is del t? So let us first define del t. Del t is equal to 1 and del t is equal to 0. When it will be equal to 1? At t is equal to 0. And when it will not be equal, and when it will be equal to 0? At t other than 0. So at particular value of del t, it is equal to 1. So how does it look like? So it looks like this. This is 0 axis or 0 or origin. So this is del t, if this is the time axis, right? So this is the definition of del t. And what is the Laplace transform of del t? Laplace transform of del t is equal to 1. Laplace transform of del t is 1. Why it is 1? Because you can use the formula, that is Laplace transform of del t is equal to, what is the Laplace transform formula? That is 0 to infinite. Okay, del t e to the power minus st dt, right? And it is equal to 1. When it is equal to 1, for t is equal to 0, and it is equal to 0 for all the other values. So you can consider this from 0 to 0 or 0 to very small value, you can say, and it is equal to 1 and e to the power minus st dt. Now you can integrate this. This will be equal to e to the power minus st 1 minus s. Just wait a second. I have made some mistake, I guess. Okay. So Just forget this different integration. For now, let us assume that Laplace transform of impulse function is equal to 1, right? And it is not exactly like this, that is that is not equal to exactly equal to 1 at 0. But if you will zoom this function, or if you can zoom this, so it something look like this. This is very small duration. You can consider this as d, and you can consider the height as a. Please mute yourself. I can hear some of the disturbances. Now area of this is equal to, you can write area of this rectangle is a multiplied by d, and this is equal to 1. So this is equal to, this is how delta is defined. So d is very small. You can say 0 to 0.000001. So if 0.00001, and if multiplication of a and d has to be 1, so a should be equal to tending to infinite. You can assume that. Are you understanding this? If, because d, that is the width of this pulse
Yes.
is very small, and area is equal to 1, so a has to be infinite. So del t is equal to 1, and Laplace transform of del t is 1. We will see this why this Laplace transform del t is 1. We will see. Just wait a second.
Sir, if the area is infinite, then specifically the height should be infinite.
Sorry. Yes.
If the area has to be infinite, then
Yes.
ultimately the height should be infinite.
Correct. Correct. Right. And people are seeing about this. That is Laplace. Sorry, Laplace transform of del t is equal to integration of 0 to infinite del t e to the power minus st dt. So, but this is only but the value of del t is only 1 at t is equal to 0. So you can put t is equal to 0 here. So 0 to infinite del 0, you can write e to the power minus s0 dt. So you can see e to the power minus 0 is again 1. So you will get this as 1. And because here limit will be tending from 0 to 0, you can keep it like this. So it is equal to Laplace transform of del t will be equal to 1.
Excuse me, sir.
Yes.
Sir, can you repeat it once more? Sir, I got disconnected in between.
Okay. Which part you have missed?
Sir, from this part, sir, after the integration of the del t.
Okay. Just remember that the Laplace transform of del t is equal to 1. This is this is the important part. So I will again recollect for all of you. We are having some of the standard signals. So first one is, you can say, impulse function or impulse signal. Second one is unit step function or step signal. Third one is ramp signal. Fourth one is parabolic signal. Right? And how to denote this? That is, it is denoted by del t, it is denoted by ut, it is denoted by rt, and it is denoted by pt. And how to define this? It is equal to 1 and it is equal to 0. For t is equal to 0 and for t not equal to 0. How you define ut? It is equal to 1 and 0 for t greater than 0, and when it will be 0 for t less than equal to 0. What is rt? It is equal to t and 0 for t greater than equal to 0, for t less than equal to 0. What is pt? You can define pt as t squared and 0 for t less than, for t greater than 0, and for this will be t less than 0. What is the Laplace transform of del t? You see, equal to 1. Laplace transform of ut is equal to 1 by s. Laplace transform of rt is equal to 1 by s square, and Laplace transform of pt is equal to 1 by s cube. So these are some of the standard signals. Why we are studying this? Because we will in future lectures or in future course we will study about the control system aspects of a plant or a system. Basically, control system, I will just give you brief why we have studied signals, because we will study systems. Let's suppose this block represents any system. This system can be your, let us just say, AC or air conditioner. This system can be your car. This system can be your refrigerator, right? Anything. We generally represent it by system. So,
Sir,
so
can you explain again the part where you like integrated the impulse signal?
this
Sir,
part,
the area part, the area part.
area part.
Yeah, like where you said, so like how can area tend to infinity? Then won't the like
Area is not tending to infinity. Area is tending to one.
yes, sir.
Area,
Like if you said A tends to infinity, right?
sorry.
You said A tends to infinity, right?
Yeah, because d is very small, not tending to infinite. If you can say if d is equal to 0.001, right, and if area is equal to 1, so what will be the a? That is 1 upon 0.00001 or 0.00. It can be 1000, it can be 10,000, depending upon what is the
Like, whatever you multiply with infinity, it would be close to infinity only.
what will be whatever.
Like whatever you multiply with infinity, it would be close to infinity.
It is not infinity, as I told you. D is depending upon what is the system, or which is from which you are getting this impulse, right?
Yes, sir.
It all
Like,
depends on
you
D.
said A, sir, A is the like length of.
You can say not A, because you are getting confused. So let us replace this A by height. You can call it as H. Okay.
Yeah,
So
but that is one, sir. Now, for impulse.
area is one.
Okay, sir. Area is one.
Area
Like
is one, right? Then that means H into D is equal to 1. So we say that is del T is equal to 1.
okay, so like we are dividing the like y-axis into two parts, right?
Sorry.
Like we are dividing the y-axis into two parts, right? H and D.
No. We are not dividing y-axis into two parts. Let me again show you. So let us suppose this is our x. This is our you can say.
So your voice is not audible.
Your
Voice
voice
is
is
not
cut.
audible.
Let us say this is our x and y axis. This is our x axis. This is our y axis. Okay. If I wanted to draw an impulse, so it will something look like this. Okay. So this distance or this space is called as, I'm calling it as d, and this height I'm calling it as a, and a multiplied by d is equal to 1 is equal to delta.
Sir, but A is also one, right? Like the magnitude of impulse signal is one.
A is not 1.
Sir,
You can,
excuse me.
sorry.
Excuse me, sir. If as area is equal to 1, so del Laplace of del t is equal to 1, right?
Yes.
As area equal to 1, so del t equal to 1.
Okay. Yeah.
Means as area is equal to 1, so
Mhm.
del t value will be
Do
1
not,
always.
you see, do not get confused with area and all. You just assume that, say that del t is equal to 1. Okay. And Laplace transform of del t is also equal to 1.
सर लेकिन
Okay.
लैपलेस करने से तो 1/s आना चाहिए था ना.
No, because why it will be 1 by s? Because if you're considering 1 by s कब आता है, जब हम लोग करते हैं लैप्लास ट्रांसफॉर्म यूनिट
डेल्टी को
स्टेप.
1 लेंगे.
और यूनिट स्टेप
Yes,
क्या
sir.
होता है, जीरो से इनफाइनाइट तक जाता है. लेकिन ये डेल्टी क्या है, सिर्फ जीरो पे ही है. It is not going tending to infinite. When it is not tending to infinite, you cannot write it 1 by s. Okay.
Okay, sir.
We have seen
Okay,
that
sir.
Laplace transform of u of t is equal to how much? 1 by s. And here t is tending from where to where? 0 to infinite.
Yes,
But
sir.
here,
Yes.
but here Laplace transform del t is equal to 1. But t is equal to 0. So at t is equal to 0 only, it is equal to 1.
Okay, sir.
Right? It is
Yes,
not
sir.
tending to infinite. Just for your reference, that I have also talked about this little bit in your unit step signal, because uh, I'm not sure how many class teachers will discuss this, because unit step, if you see in the book, it will usually look like this, right? It starts from 0 and it goes to infinite. But if you can zoom it for practical application, in practical application, if you can zoom it, so it will something look like this, right? So
Yes,
this
sir, you
amount of
told me.
delay has to be there. There is no system which can provide instantaneously magnitude of 1, right? At 0, if you switch on something, it will take some amount of delay. Is it now okay?
Yes, sir.
Now,
Yes, sir.
for delta, earlier I have shown delta, and delta is equal to 1. This looks like this, right? We generally write it as 1. We generally write delta is equal to 1. But if you can zoom it, if you will zoom it, you will find it that delta is also having some this kind of a rectangle, where this is having d and this height is equal to h, and the multiplication or area of this is equal to 1. Now is it okay? Okay, so
Yes, sir.
we will
Okay, sir.
discuss
Yes,
it
sir.
when we will be using this. Okay, now let us come to the point where I was talking about why we are discussing about these signals, right? So I was talking about, let us say that we have a system in control system. We are having a system. Let us suppose this block represent a system, right? The system can be your car, can be your AC, can be your fridge, can be your anything which you want to control, right? And this is your input to the system. I am writing IP for now because it is starting. Let me write input, and this will be your output. Generally, output is written by O/P. Input is written by I/P. Okay. Let us suppose this is your system. AC and this can be any of your system. So, what is why we are discussing this LT, UT, RT, and let us say PT also. Why we are discussing this is that when you develop a system, when you are a manufacturer, right? When you are into research domain, when you develop the system, then this system at laboratory cannot be exposed to real time world. That real time, you can say, or real time environment, right? In real time environment, there if you are having a car or a bike, you have to you can the bike or car can be has to be gone through the breaker. It has to be gone through that path hole, right? It can be suddenly stopped, it can be suddenly raised, accelerated, whatever, right? So that is real time environment. But when you're developing any system in the laboratory, right, in that laboratory you cannot have a real time or real life experience or real life environment. So in that way, this impulse signal plays a very important role, where we provide this simple
So your voice is not audible, sir.
Can you please repeat the last line? Because your voice is not audible at that time. Last line.
okay. Am I audible now?
Yes, sir.
Yes, sir.
All of it? Okay, so I was talking why we are discussing these signals, right? We are discussing these signals because if you develop any system, that system, in order to test that system, in real life, many situations may arise. Like if you are having a bike, that bike uh, can have a maximum speed limit of, let us say, 120 hours per kilometers per hour. Then when you are running at a certain speed, you can suddenly brake. You have to make it pass through a breaker. You have to make it pass through a path hole. There are different real life environment, right? But in laboratory we are not having that facility or that environment, right? So in order to test our system to that environment, what we did or what researcher will did has done, they have developed some signals. These are the basic signals like delta. Now your system will be exposed to this signals. These signals are called as test signals. These signals are called as test signals. And once your system is test signals, means you can assume that this is the input to your system. To this input, your system will perform some of the output, some output, right? We can say if you provide, let us suppose that you are providing here UT. Let us suppose that, again I will draw. This is our system. Let us suppose that I am providing a UT in our system, and some kind of response our system is producing. Let us suppose we do not know what is the response. So let us just write CT. I will put it here question mark. Okay. This is our system. We have provided a step input to system and we do not know what is the response. So this is the whole control system. We will see in following lectures what is CT, and looking at CT, how can we judge whether the system is able or capable of doing certain task, right? And similarly, if like UT, we can provide here del T, we can provide here RT. What does RT look like? RT, if you're talking about bike, what does RT look like? Means if you press your accelerator linearly, your bike speed will increase linearly. What is UT look like? Suppose if you want to maintain 80 kilometer per hour in your bike, you will hold acceleration to a point where or you might have also heard about cruise control in today's world, or today's car. In that, a constant input is given to the system so that it is able to maintain 80 kilometer per hour. Suppose if you want to increase your speed from 80 kilometer per hour to 100 kilometer per hour, let us suppose that you will provide RT here. Now, what is the use of PT? PT, if you are at rest, that is 0 kilometer per hour, and if you suddenly wants to reach at 100 kilometer per hour, that is sudden acceleration you want. So, what kind of input you can imitate from the real world environment to the laboratory? You can expose your system to PT. PT means parabolic. It means sudden acceleration, that is 0 to 100. Are you getting my point?
Yes, sir.
Suppose you are running at 150 kilometers per hour again, and red light comes or breaker comes when you suppose you have not seen breaker from far away, and suddenly you see that there is a breaker. You want that your system should stop. In that case, you can provide del T. Or another example of del T is, suppose you are using a hammer. You are using a hammer on a nail, right? And you provide or you hammer that nail into the wall. So that hammering, you can assume it to be del T. Now let us suppose what is the time duration when you pick up the hammer and you are pushing or punching in the nail. So that time duration is very small. That you can say that millisecond or microsecond. Like 1 millisecond, it can be 1 millisecond or it can be 1 microsecond. So that is, you can refer as a del T. So we are using this, again, I am telling you, we are using this standard signals. These are standard signals, that is UT, del T, which are available at our laboratories for research purpose. And you can make any signals. Again, I will repeat. You can make any signals of any nature from these 4 test signals, right? Let us suppose that you want to make. You might have already studied this in signal system. Let us suppose you want that your system should be exposed to this kind of signal or this kind of system where you are at rest and you are providing acceleration, then you are maintaining a constant speed, and then you are deaccelerating, and then again you are at the rest. Suppose if you want that your system should be exposed to this condition, so you can make these by the help of this. Have you studied this case? How to make this from these test signals?
So by
Yes, sir.
combination of ramp, unit step, and
A
impulse.
combination,
Right.
of RAM.
So you have already studied, but I'm not sure whether you have studied the practical aspects or not. Okay, you might have already you might have studied how to make this signal, but where to use these signals? Ultimately, this signals has to be used somewhere. Therefore, we are studying this. So this,
Yes, sir. Right.
yes, please ask. So this is why we are studying these test signals, right? So these test signals are very important. So that is why from starting you have to know it very clearly. That is, this is del T. This is
Sir, sir, actually, I have a doubt regarding the system. Sir, in the system, when you talked about the vehicle accelerating, we were using ramp signal. Sorry, I mean the exponential signal.
yes.
And when we will be applying the brake, we'll be using the So can't we use a negative exponential signal while applying the brakes, because the magnitude of time that it will take to accelerate and then to decelerate in order to stop will be, I mean, the reciprocals, isn't it? You use delta while applying the brakes. That I couldn't understand.
That I've just given for your you can say you can think on that on this part. I'm not
Okay,
saying that
okay.
exactly delta will be given, right? I'm not saying exactly this function will be given to have this kind of output, right? I've just
All
given
right.
you a window
Yes.
to look into it, right?
Okay, sir.
I've just,
Yes, sir.
I've just shown you the path. Yes, why we are studying this signal, because these signals I've just talked about the two example, like hammering. We we refer input as del t, we refer
Yes, sir.
this delta, and we have some output, right? So these
Yes, sir.
kinds of signals are useful in laboratory, very useful in laboratory. With the help of these signals, we can actually imitate a real world environment. That is the whole thing that I wanted to convey to you guys. Do not assume that all the things that I have taught here is exactly what is happening, right? Do not think
Yeah,
in
yes, sir.
this,
Okay, sir.
but just think is in this way that yes, any system which is developed by big multinational companies, any system, like let us suppose for that case bicycle, let us suppose for that case refrigerator, a car is you I'm not sure whether you will be knowing that or not. A car before coming onto the road goes to certain safety environment or safety precautions. It is immersed in water for I think 1 week, and they see whether there is a effect of any rusting and all. And so these are uh, various ways to test our systems which we are developing, right? We cannot just put four wheels on anything and come to the road. It is not right. Okay, it is not like that. So this is how your system works, and this is how or this is what the usefulness of the signals. These are some signals that I want to talk about. We will study this again when we will revisit or when we will study our control system in details. At this starting point, I've just explained you what are these systems. Sorry, what are these signals, right? What are its characteristics? What are its Laplace transform? So I have told you everything. Again, we will be discussing this again later on in our lectures. Let us move forward.
Sir,
Yes, please ask.
excuse me, sir. No, can we apply this signal to our any TVs, mobiles, my developing mobiles, TVs?
Yeah, you can without this signal, without testing. See, there is a testing department at every manufacturer. So obviously, okay. So now we will again look at the inverse. Till now we have covered the Laplace transform, and now we will see some of the examples of inverse Laplace transform. Again,
Sir, your
सर
voice is
आपका आवाज
too
नहीं आ रहा
low.
है
okay, we will see an examples of inverse Laplace transform. Am I audible now?
Yes, sir.
Right now I'm in university. I thought that the tower here will be good. Anyway, so we have already seen how to take the Laplace transform, and I have also provided you the notes for inverse Laplace transform. We will start with this very small examples, and then we will move towards not very hard, but we will go up to the point which is required by this control system course. Okay, we will not be dealing deeply in what is inverse Laplace transform, deep or complex mathematics. We will just be seeing the part which can be easily utilized in control system. Though control system itself has a very complex mathematics, but we will not be involving very complex mathematics as far as this control system course is concerned. If you want to go for higher research, if you want to go for masters and PhD, the control system consists of very complex mathematics, right? A very high order mathematics, you can say. But for this course, we will not be dealing with that complex. All the things are based on concepts. The important thing is that you should learn concept, and then you can obviously, if you have interest, you can go for further studies as well. So we will see some inverse Laplace transform by the help of an example. Let us suppose, am I audible?
Yes, sir.
Yes, sir.
X of s is given by 1 upon s plus 2. Again, I'm taking this from the notes that I have provided to you. So what will be the inverse Laplace transform of inverse Laplace transform? I will wrote it by L inverse, right? L inverse of x of s will be given by x of t, and and this will be equal to Laplace inverse of 1 upon s plus 2. What will be the Laplace inverse of 1 upon s plus 2?
power minus
e
2s.
to the power minus 2t.
To the
E
power
to the power
minus
minus 2.
minus
E to the
2t.
power 2t, not 2s. It will be minus 2t, right?
Yes, sir.
So slowly we will go to the next example. That is x of s is equal to 6 upon s square plus 2s. So we have to take the inverse Laplace transform of this, right? So how to proceed? So let us again write xs is equal to 6 upon s square plus 2s. First thing is that I have talked about the common signals. If you recollect from our starting classes, you have to see in this problem whether this Laplace transform, which is already there, is in the format of our common signals that we have studied. Is there any is there the Laplace transform of any common signal which results in s square plus 2s? Is there any signal?
No, sir.
Yeah. So what we will do, we will take 6 upon s
Yes,
common from the
common.
denominator, s plus 2, right? Now if we can separate 6, let us suppose any function by any constant, if we are able to separate this, now if we are able to do that, then it will be very easy for us to take the inverse Laplace transform. So next step is, what we will do is we will take the
सर
partial,
ऊपर s प्लस 2 माइनस s कर देते हैं तो फिर हो जाएगा 6 इंटू ब्रैकेट के अंदर s प्लस 2 माइनस s,
right? That is,
और
we will see what
बाहर 1/2 कॉमन ले लेंगे.
yes, we will see what we will do. But the first thing is that, first thing you in your mind should be that we have to do partial fraction. So I will tell you just one time in this whole course how to take the partial fraction, because it is you might have studied in your school days. Also you might have studied in signal system, but again I'm telling you, those who are not aware. So 6 upon s into s plus 2 is our fraction. Let us suppose, since there are two fractions, that is s and s plus 2, so we will divide it into two categories, a upon s, b upon s plus 2, right? Now if we take the LCM, so this will be 6 upon s plus 2 is equal to a s plus 2 plus b s upon s into s plus 2. So this s plus 2 will cancel, and we will be having 6 is equal to a s plus 2 plus b into s. Put s is equal to 0. So if s is equal to 0, b is equal to 0. So a will be equal to how much? 3.
3.
If put s is equal to minus 2, why we are putting s is equal to 0? So that b should be equal to 0. Why I am putting s is equal to minus 2? So that a will be equal to 0. Now if I put s is equal to minus 2, a will be equal to 0. And what is the value of b?
-3.
Minus 3.
As 3, right? So we have taken, so x of s I can write as 3, that is a, that is 3 upon s minus 3 upon s plus 2. You can just check it if that's correct or not. Let us assume that this is correct. Now you have to take the inverse Laplace transform of x of s. So 3, what is 1 by s? Inverse of 1 by s is 1 minus
Yes,
3
sir.
e to the
3
power,
minus 3 e power minus 2t.
right? If you want, you can write whole multiplied by u of t. There is no harm in writing u of t. What does u of t means? U of t means, first thing is that the signal is only valid for t greater than 0. It is having values for t greater than 0. And what is the value of u of t for t greater than 0?
1.
Is 1. So if you multiply anything with 12, will be that function only. So you can multiply in this way, so that it will be much, this looks in a good way. So 3 minus e to the power minus 2t into u. This will be the Laplace transform of your x of s. Is it okay?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Next example we will see. Again, h of s is equal to 1 upon s plus 1. s plus 2. So this is again not in from our common signals, not in any of the standard format. So what we will have to do, we have to do partial fraction. So again, I'm just directly writing now. You can see 1 is equal to a s plus 2 plus b s plus 1. Now put s is equal to minus 1. If you put s is equal to minus 1, b will be equal to 0. So a will be equal to how much? 1. And if we, when you put s is equal to minus 2, so a will be equal to 0 and b will be equal to how much?
1.
Minus 1. Minus 1.
Minus 1.
So h of s will be equal to how much? 1 upon s plus 1 minus 1 upon s plus 2. Is it okay? The Laplace inverse of h of s will be equal to ht. This will be equal to, what is the Laplace inverse of 1 upon s plus 1?
E
e
to the
power
power
minus
minus
t
t
minus e power minus 2t.
minus e to the power minus 2t.
And write here into 2 of t also, if you want. So now we will discuss a little bit about poles and zeros in between. Poles and zeros. So poles, you can see in the notes also, poles is the root of denominator. Poles is root of denominator. Poles is the root of denominator, and zeros is root of numerator. Poles is the root of denominator, and zero is the root of numerator. And how we represent poles and zero? Pole is generally represented by cross sign, and zero is generally represented by small circle, right? So again, if I talk about this transfer function or this function, so since this is in Laplace transform means this is in S domain. If this is in S domain, that means S consists of two parts. S domain consists of two parts, that is sigma plus j omega. This is our real part, and this is our imaginary part. Okay, that means this is our real axis, and this is our imaginary axis. Is it okay now? Till now, it is okay?
Yes,
Is it
sir.
okay?
Yes, sir.
Yes,
Okay.
sir.
Okay.
Yes.
Now, can you tell me what are the roots of the denominator here?
-1 -2.
Yes. How you will find the roots of denominator? You will equate denominator equal to 0. That is s plus 1 into s plus 2 should be equal to 0. This is how you find the roots. So s plus 1 will be equal to 0 and s plus 2 should be equal to 0. So s will be equal to minus 1, s will be equal to minus 2. So there are two poles, and these two poles are real poles. You can see minus 1 and minus 2, they are having 0 imaginary part, that is j0, j0. Imaginary part is 0. How you can represent these poles in your x-axis, in your s plane? Let us suppose this is minus 1 and this is minus 2. So this is how you represent poles and zeros. Are there any zeros in this h of s?
No.
You can see there are no zeros in h of s.
No.
It is equal to constant,
No, sir.
right? We will move again upward little and we will see whether. Now let us say this is our answer. This is our function. Again, can you find?
Your voice is again cracking.
Okay. So let me again draw S plane. This is our S plane. This is our real axis. There is sigma, and this is our j omega. Right? Can you tell me what are the roots of denominator?
-2 and 0.
Okay. How we are finding that is s square plus 2s. Put
Equals
again
0.
denominator equal to 0. So s will be equal to s plus 2 will be equal to 0. So you can see s will be equal to 0 and s plus 2 will be equal to 0. So s will be equal to minus 2. So there are two poles or two roots. So therefore we will say there are two poles. Why we are saying it poles? Because both are in denominator. Okay. So how can we represent this pole in S plane? One pole is at origin. You can say why it is at origin. So because S is equal to 0, you can see. And one pole is at minus 2. So minus 2 and this is 0. So this is how you represent poles and zeros. In coming example, we will see how to represent zeros as well. Right now, we are not having zeros in any of the examples. So we will move forward. So now let us take another example. That is x of s is equal to 4 upon s square plus 3s plus 2. Now you have to see whether this is any of the standard format. You have to check. So you can check later on. I will, because of less time, I will be just solving this. So you have to first divide it into fractions, or you have to calculate its roots. How you can calculate its roots? The formula is minus b plus minus under root of b square minus 4ac upon.
सर x of s will be 4 by s plus 1 into s plus 2, उसके बाद partial fraction कर देंगे, हो
Yes, 4
जाएगा।
upon s plus 1
4 will be s plus 1
s
into
plus
s plus 2.
into partial fraction. Okay, I will be directly writing some its results. Let me write here question mark. You have to find this question mark. So this will be e to the power minus t plus or minus e to the power minus 2t. Okay, you can find out its inverse Laplace and how to represent its poles and zeros. So this is S plane.
So poles will be minus 1, minus 2.
Poles will be at minus 1 and minus 2.
Minus 2.
This is minus 1. This is minus 2.
No zeros are there.
No zeros are there. Correct. We will see. Take another example. Let me take little. I can say.
Sir, can you show any example of zeros where we can find out zeros?
Okay, you want to. Okay, just for just because he has asked one problem, I will be not. This is not for exactly for inverse Laplace. I'm just giving you example how to look at poles and zeros. So let us say suppose that we are having a function that is t of s is equal to s plus 1, s minus 1, s square plus s 4 whole divided by s plus 2 s square plus 6s plus 9. Right, we are having this function. Let us multiply this also, s plus 10. This is a function where we have to find out its poles and zeros. Can you first look at what are the zeros? Zeros are at
1 minus 1 minus 2.
1 plus 1 minus 1
Minus 1 and minus 2.
Why minus 2?
Sir, s square plus 4s plus 4.
S square plus 4s plus.
S plus 2 whole square, that's why.
So this is what? S plus
S plus
4.
2 whole square.
So there are two
Yeah.
roots. There are two roots at
Minus 2 and minus 2.
There are two roots. Just keep this in mind. There are two roots. Okay, because this will cancel. So let me write here 3. Okay, s plus 3. What are the poles here?
Minus 2, minus 3.
Minus 2, minus 3, minus 3, minus
Not
10.
minus 3 only. Minus 10. And this is how much?
Minus 3.
Minus 3 again. So minus 3 and minus. So minus. There are 3 poles at minus 3. You can see. There are 3 poles. 2 poles are here and 1 poles are here. How to represent it in S plane? This is our S plane. There is 1 0 at plus 1, so I can represent it minus. So this is 0. 1 0 at minus 1, so this is another 0. And two zeros at minus 2, so this is minus 2. Let us suppose I'm writing at this, right? This is minus 2, minus 1, plus 1. And how can I represent poles? 3 poles at minus 3. This is first cross, this is second cross, and this is third cross. So this is minus 3. And there is one more pole at minus 10. So this is minus 10. So this is how you will represent minus poles and zeros. Now let us suppose that after finding out the roots.
Excuse me, sir.
Yes, yes.
Sir, are the poles and zeros both will be represented along the x-axis?
Yes, because all the things are real. You can see that is what the next point I'm considering, right? Let us suppose these are the roots. Numerator roots are zeros, and denominator roots are represented by poles, right? If you're finding out roots, there might be some case where that roots is complex. There is, let us suppose, plus minus J2, and let us suppose poles are at minus 2 plus minus J3. Let us suppose this is the scenario. Okay.
Yes, sir.
So how to do this? Again, we have to draw S plane.
It
This is
will
a
be along y axis, both the pole and
yes,
zeros.
yes. So let me divide this. Let this be minus 1, minus 2, minus 3, minus 4. This is j omega axis, right? J omega. This is j omega, 2j omega, 3j omega, 4j omega. This is minus j omega, minus 2j omega. Are you getting this? Minus 3j omega, minus
Yes, sir.
4j omega. Now, can you tell me where is the zeros? You can see minus 2 plus minus 2j. Minus 2 is this point, and plus 2j will be here, and minus 2j will be here. Similarly, you can see where are the poles, minus 2 plus minus 3j. So this is my pole, or I will use different color. So this is my first pole, this is my second pole. Are you getting this?
Yes, I understood, sir.
With this, you may have poles and zeros at another point, that is minus 3 and minus 4. Suppose this is the condition. So this is how you can represent minus 3 and minus 4. Okay. This is
Okay,
just
sir. Got it.
so we will take another example.
Sir,
Yes.
so when we are analyzing quadratic or cubic equations for finding out the poles and zeros, so when we get points, I mean, we get multiple points at a single place, so then we have to represent it with double cross and double circles, or like the
Yes.
way you
Yes.
have done above.
Yes. Correct.
Okay.
Because the evaluator will never come to know that you have shown. If you have represented 3 cross, just takes little bit space, then you can represent 3 dots, right? Like
Okay,
this.
sir.
आवाज नहीं आ रहा आपका
Like there are 2 zeros and 3 poles, you can represent it like this.
Yes, sir. Okay.
Okay. Let me take another example. So partial fraction, all of you can do, right? Should I move forward?
Yes, sir.
So let me take another example. That is, let us say that a function that is f of s is given by 6s minus 5 upon s square plus 7. Am I audible?
Yes,
Yes,
sir.
sir.
Yes, sir.
yes sir
Yes. So you have to find the inverse Laplace of this. Inverse Laplace of f of s. So how will you do that? Anyone?
Sir, at first 6s by s into s plus 7 minus 5 divided by s into s plus 7. तो s मतलब दोनों पार्ट में डिवाइड हो जाएगा. सर दोनों पार्ट में डिवाइड हो जाएगा. एक 6s के साथ आ जाएगा, एक 5 के साथ आ जाएगा. तो फर्स्ट वाला मतलब नॉर्मली हो जाएगा और सेकंड वाले के लिए पार्शियल फ्रैक्शन करना पड़ेगा.
No, there is no multiplication of s in the 7. You can see. You cannot take common. This is not.
No, sir, I am telling that f of s equals to 6s divided by s square plus 7 minus 5 divided by s square plus 7.
6s divided by s square plus 7 minus 5.
Minus 5 divided. तो
Then
फर्स्ट पार्ट में सर 6s डिवाइडेड बाय s into s plus 7. सॉरी. हाँ. दोनों में पार्शियल फ्रैक्शन करना पड़ेगा. हाँ सर.
how will you do partial fraction? Partial fraction, how will you do?
सर
So one way it can be done, sir.
Yeah, tell me.
yes sir.
Sir, if we can split 7 as 9 minus 2, तो s square plus 9 आएगा.
Okay,
हाँ
just
सर.
check.
अगर
Just check. Okay. Just check what I'm writing. Laplace transform of sine t and Laplace transform
सर
of cos t. So Laplace transform of sine t is omega, or omega right now is omega is 1 here.
ओ
This will be
हाँ.
equal to 1 upon s square plus 1, and this will be equal to s
Yes
upon s square plus 1. Right?
sir.
So
Yes.
I can write here 6s upon s square plus under root of 7
Root 7
square
7 square.
minus 5 s square plus under root of 7 whole square. So you can see s
Yes
term is
sir.
here and s term is not present here. So that means this will belongs to cos term, and this will belongs to sine term. And
Yes
let's
sir. Yes
see
sir.
how I will be doing this. So 6 So this
Sine.
you can take,
Cos. Sorry.
you can take this as a cos, right? So this is cos under root of
Root
7
7
70
t, right?
t
minus
Minus
5
minus
sine root
5,
70.
and if you can
root
multiply
5
7.
cos,
under root of
5
7
cos,
and
root
divide
70.
by under root of 7, so this will be 5 under root of
Yes, sir.
7 sine under root of 70. Is it okay?
Yes, yes,
Yes,
sir.
sir.
Yes, sir.
Okay. Let me take another example of the, so f of s. We are having classes from 4.
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Just wait, 2 minutes are there. I will complete this last example. S square plus 8s plus 21. How to complete this? How to calculate the inverse of this Laplace transform?
So
Anyone?
first तो इनको
S square
factors.
plus 8s plus
Yes.
21. This is our denominator. So we will try to do that. So this we can write it as s plus 4
S
whole
plus
square plus 5. If I will write, can I write it like this?
Yes, sir.
So
yes,
f
sir.
of s, again I can write 1 minus 3s upon s plus 4 whole square plus 5. So you can see this is again cos and sine term, but there is a shifting in s
Yes,
plus 4. So
shifting.
this can be used or done by multiplying exponential term, right?
Yes, sir. To the power minus 4.
Yes. So but I want s plus 4 term. So I can write 3 into s plus 4 and minus 4. I can write it like this upon s plus 4 whole square plus 5. Is it okay? Just let me know if I make any mistake. So I can now I will take 3 common. So minus 3 common. So s plus 4 whole divided by s plus 4 whole square plus under root of 5 square. And what is the remaining term? This is minus 1. Sorry, plus 1 minus 3 into minus 4. Minus 3 into minus 4. This will be equal to plus 12. Plus 12 plus 1 will be equal to 13. So plus 13 divided by s plus 4 whole square plus under root of 5 whole
Root 5
square.
whole square.
So we will multiply under root of 5 numerator and denominator, right? To make it in sign term. So this will be equal to minus 3
Yes.
e to the power minus 40 cos t, sorry, cos under root of 5t plus 13 under root of 5 sine under root of 5t. Is it okay?
Yes,
So
sir.
e to the
Yes,
power
sir.
minus 40 will also be here. Is it okay now?
Yes, sir. Got it.
So we will stop here.
Yes, sir. Yes, sir.
So this completes your Laplace, the introductory class part. Now we
Sir,
will.
can you please show the previous numerical ones?
Next one.
Yes, sir.
So will you be
Okay,
sharing
sir.
the
Done.
recording of the classes, sir?
Okay, I will be sharing that. Okay.
Okay, thank you, sir.
Okay. So in this example, you can see we have done nothing, but we have first separated 6s and 5. So this 6s and 5 we have separated. So this s upon s square plus under root of 7 comes into the cos term, and this comes in sine form. If we want that to come in sine form, so we have multiplied and divided by under root of 7. You can see here. So division is coming in front, and multiplication of 7 is coming in sine form, and this is coming in cos form. Okay.
Yes, sir. Understood, sir.
Let me take the attendance quickly.